Hello and welcome to Color Management Fundamentals and ACES Workflows in Nuke. This is Victor Perez for Foundry. This series of video tutorials is aimed at anybody involved in visual effects at any position, but especially, of course, for Nuke artists. Here you are going to understand the elements of color workflow at a scientific level, in order to set up a consistent pipeline according to the project in relation with other departments, inside and outside visual effects, from camera to screen, so everybody is aligned to the same standards, preserving color qualities, consistency, and maintaining the artistic intent. For some examples later in this course, I'm going to assume you are already familiar with Nuke compositing. I'm not going to explain basic functionalities of the software, and we are going to explore how to implement your pipeline using Nuke Studio, which has been specifically designed for this purpose, irrespective of whether you are an individual working with others or a facility to establish the color workflow site-wide. So, let's start. We are talking about color management, so let's be clear about this concept up front. Color management is a protocol of control conversion between the color representations of various devices to keep all departments aligned to a common vision by providing consistency in image reproduction and creative intent. Wow! That's a very wordy explanation, and it's exactly that indeed. In other words, a way to ensure everybody, everywhere, is seeing the same image on their respective screens, and not just in any way, but the way the artist working on those images intended to show. The principle is simple. You see what I see, and we both see the right image. It may seem trivial, but believe me, for many reasons, even historical reasons, it's quite a complex subject. Why? Well, let's wind back our clocks a few years, at the times where digital film cameras weren't invented yet, and we simply use film negative to shoot. That was later developed and then scanned, seen on files, do you remember? Oh boy, I think I'm getting old. Then, on the other hand, you had computers generating renders, linear images, and other digital media coming from Photoshop or other sources, generally all using the same standard RGB format. Those times. Log, link, and gamma encode media that you comp together and then you deliver either for cinema or broadcast. That's it. And we thought that was already complicated because you had to keep in mind we were mixing 3 different color spaces and usually different bit depths as well, and other factors. Today, things are radically different. Even though the tools we use allow us to work smarter, you need to know clearly what to do and how to do it. As always, the artist is in command. There are things that you simply cannot skip. Yes, we still use film negative cameras combined with computer images, as we did before, but the element that has truly revolutionized the media entertainment industry from the point of view of acquiring images is the digital camera. There are so many different manufacturers and camera models, each one with their own way to encode light, and I mean different color gamuts and transfer functions. In other words, different color spaces that we have to add to the previous ones we saw earlier from a few years ago. No worries, we are going to demystify all those concepts I just mentioned. But cameras are not the only innovation from this new era of digital media. How we watch contents has evolved as well. Analog cinema projections still exist. Sure, you can ask Mr. Christopher Nolan about it. But we all can agree the mainstream is digital. Cinema or TV, that is now digital as well. And not only, there are different versions coexisting. Standard definition, high definition, ultra high definition. Each of those with their own color spaces. And then high dynamic range TV and projectors, both for home theater and cinema. And computers, of course. And the superstar of all devices, mobile phones and tablets that stream contents directly from these guys here, whose standards need to meet all the above. We have to ensure everybody delivers the same high-quality standards, an even more complicated task when you have different facilities working on the same show or even on the same shot. Every color counts. So let's start breaking down the problem from the top. How we capture images. Film scans are always the same. Then let's focus on digital cameras. These are a few examples of the most popular digital film cameras. The first thing you are going to notice is each one has a different representation of light. Those are the clips without any correction applied to remap the colors to the right place and see the image as intended by the manufacturer, what we can call the right color. Each clip has its own color space, specifically designed by the manufacturer to optimize the fidelity of the colors the sensor is able to reproduce, mapping the linear 3 stimulus values and the non-linear electronic signal. In order to comprehend all of this, we need to understand the foundations of color spaces. A color space is a specific organization of colors originated from the combinations of the color components from a color model. It can be arbitrary by assigning just a name, like in the Pantone collection, for instance, or defined within a mathematical structure, for instance, a set of coordinates. So we have to see color spaces as that, a space to lay out the address and identification to each single color available to be reproduced by a given device, either to capture or to reproduce. There are several color models, depending on their use, like the CIE, that studies the human perception, the CMY or CMYK for ink, which means printing purposes. This one uses a subtractive synthesis, meaning all the components together gives you black. The RYB, used for painting pigments in art and design, the one where yellow and blue makes green, remember from school? Others are more familiar for us VFX artists, like the hue, saturation, and value, or hue, saturation, and luminance, that is a structure in polar coordinates on a cylinder. And the instance that interests us the most for this purpose, the RGB model, the additive synthesis of light, where all colors together gives you white. Our color spaces for displays, cameras, and post-production all use the RGB model. The reason we use the RGB model is because cameras and displays had been created using as a reference human color vision. So let's get to the bottom of how humans see color. Inside the human eye, we have 3 different photosensitive cells that capture different wavelengths of light. The span of those wavelengths of light is what we call the visible spectrum. The average range goes from 380 to 700 nanometers. So if we lay out the wavelengths as a continuous mix of colors, we have the ability to navigate through this spectrum in one dimension, one line, even though we are missing a group of colors here. Where are my purples? Did you notice those were missing? No worries, it's fine. They are just not represented by a single wavelength of light. Magenta is what our brain visualizes when the small cone cells that capture what we perceive primary as blue are stimulated together with the large cone cells that capture what we perceive primary as red, with no stimulation of the medium cone cells in charge of visualizing the green. That is when magenta appears in our brain. So if we want to mix the stimuli from all three cones, what we call three stimuli, we have to put it in a way we can have all colors able to be represented. Let's convert, then, the visible spectrum into a color wheel, so we can move in 2 dimensions. I'm sure you are way more familiar with this visualization of color. And by the way, notice this arc contains the purples we were talking about. What we have in the circumference are all the available colors at their maximum intensity. This has a name, hue. And you can find this color manipulator in any RGB slider set in Nuke. So in this model, we can define the first line of the address of a color by a degree angle of this circle. 0 degrees is red, 110 degrees is green, 220 degrees is blue, and at 360 degrees, we are back at red again. Still, the address is incomplete because we are just running on the edge of the color wheel. So we need a control to move in the direction of the center, to mix our samples with the other opposite colors. This control is the saturation, and it's the second piece of information of the address of the color sample. And yes, you have this control next to the hue in the HSV sliders. Those are the manipulations based on the hue, saturation, and value model. Notice that we are talking about color without taking in consideration the luminance or brightness of the sample. Just purely color. No matter how dark or how bright it is, we refer to these luminance agnostic colors as chromaticity, a 2D sample. In this example, a hue and saturation sample without the brightness component. The only problem is that we don't perceive all colors the same. We are more sensitive to certain wavelengths than others, and that directly affects the luminance of each color. So instead of using the color wheel, which is a theoretical and mathematical representation of chromaticity with an equal distribution of hue and saturation of the RGB model, let's organize these colors in a space that has been studied to accommodate the wavelengths of light from the visible spectrum, keeping in consideration the perception of the amount of colors and their respective luminance component. This is a Cartesian diagram with both its x and y axes format from 0 to 1. So we can recall a sample based on its x and y coordinates. That set of 2 coordinates, by the way, is called a tuple. The y-axis, the vertical one, will be used for 2 different purposes. One is to be coupled with the x-axis coordinate to define a point in the diagram. And the other use is to indicate the luminance of the sample. So the higher the luminance, the higher the value in the y-axis. This is the reason why you will see many times the luminance component in different systems referred to as uppercase Y when talking about certain color spaces. For instance, YCBCR. Some diagrams even state this particular set of coordinates as XYY with the last letter uppercase to evidence the double purpose of the y-axis, even though the position of the samples will be reported with just a tuple of 2 coordinates, as usual. Let's go ahead and place all the wavelengths of the visible spectrum according to this diagram of human perception of color. So if we combine all those wavelengths, we will define all visible colors by the standardized average human vision and their luminance contribution. This is known as the spectral locus. This diagram was the result of research done in 1931 by the International Commission on Illumination, or CIE, the initials of their original name in French. So this is called the CIE-XY chromaticity diagram, and it's going to put us and our color spaces in the context of human vision. First of all, remember I mentioned there was a specific portion of the color wheel that doesn't correspond to any wavelength, and still there is color there. This line at the bottom is named line of purples. The color exists, the wavelength doesn't. Another thing that is going to seem familiar is the hue that runs around on the edges of the spectral locus. But unlike the color wheel, that is a perfect circle, in here we have to arbitrarily define where the center is. We will talk about this later in this course. So from that center to the edges, we have something quite similar to the concept of saturation, but in the spectral locus, we call it purity, which refers to the predominance of one single pure wavelength. By the way, you cannot have purity towards magenta, because there is no wavelength in the line of purples. But you can have saturation. See the difference? Well, this chromaticity diagram is actually a color space, and not just any color space. It is our reference color space that we will use to put our RGB color spaces in relation to human vision. I think it's time to introduce a concept we are going to use a lot for color management: gamut. The spectral locus of the CIE-XY chromaticity diagram represents the color gamut of human vision. So all samples that are located within the spectral locus will be within the color gamut of human vision. In other words, colors we can see. And those samples that are not inside will be out of the gamut. Still, those samples exist in a mathematical way. We just cannot see them. This is an important concept to understand, as we will study color gamuts that will comprehend values outside the spectral locus. I think it is a good idea to briefly discuss what exactly is a gamut. A gamut is the whole available range of something defined, and I mean all the values contained in the span, from end to end. In our case, it will be color, so all colors defined within a certain range. But in this simple example we are about to discuss, we will use just numbers. This is an infinite straight line. From that line, we are going to define a segment to give us scale. So we have a lower limit and an upper limit. Let's assign value 0 as the lowest and value 1 as the highest. This is going to be our reference range. This defines our scale. Once we have the layout of scale, we are going to establish the range of our target gamut. For instance, from value 0.35 up to 0.65. This red one will be our gamut. As you can see, it is expressed in absolute terms, as we are using a defined numerical scope specified by the scaled reference. And so, all values between 0.35 and 0.65 conform our gamut. In this instance, we have a one-dimensional representation, a progression of numbers in one single axis, one line. Now, let me point out something interesting to note. Think about what we call the reference range. Isn't it itself a gamut, reference to the first gray dashed straight line? The only difference is that our reference range, the white line, was relative because we positioned the values arbitrarily in relation to the dashed line, while the red gamut was established in absolute terms using the numerical scale we define for the reference range. So let's do something. Instead of calling the white one reference range, we can call it reference gamut. This setup is very similar to the way we express color gamuts in relation to the chromaticity diagram. You'll see this in a moment. But right now, we are using only one dimension, and our diagram for chromaticity is two-dimensional. So, let's have a look at 2D gamuts. Now, our reference gamut, or reference range, is defined by two axes intersecting at the center. And so, we have all directions of the plane available. The gamut now won't be a line, but an area defined by coordinate points originated from the center. Those points will establish the vertices of a polygon. Its area is our gamut. In this case, the polygon has 3 vertices, a triangle. So all coordinates of this diagram that are inside the red triangle belong to our gamut. Let's apply this principle to color spaces. And so, we talk about color gamut. The color gamut is going to represent the amount of colors from the chromaticity diagram that a certain device can capture or reproduce. This is going to be the area of a given color space. A gamut is defined by 3 points, but this color gamut is going to be incomplete if we don't define a 4th point that is going to set its center, the point of lower saturation of the color space, which we will call the white point, something we are going to discuss later. We have the chromaticity diagram, that is the reference gamut, and we have the triangle we define as our color gamut, which is, by the way, within the spectral locus. That means this color gamut is entirely visible by humans. Then, we have the reference color gamut, which is a relative gamut. Relative to what? Relative to the average standard human vision. And we have the target color gamut, which is an absolute gamut, because it is laid out in mathematical values in the Cartesian plane defined by the chromaticity diagram. In brief, a color gamut indicates chromatic intensity, which we have called chromaticity, set the limits for the reproduction ranges of colors, and defines two things. One is the potential chromaticity reproduction capability of a given output device, for instance, a monitor, a TV, or a projector, or the other, the potential chromaticity processing capability of a given input device, for instance, a camera. The gamut is one of the fundamental components of the color space, as it defines the actual space boundaries. But before going deeper into our RGB color spaces, I think we should analyze further the chromaticity diagram, as it will define several aspects of our color spaces. Before I mention the center of the color space, the point of lowest saturation, it will define the aspect of the white color, which is, as you probably know, all colors manifesting at their maximum intensity. But that center is arbitrary, and usually is going to be calculated within a particular range of values, the arc known as the Planckian locus. It represents, within the spectral locus, the path that the color of an incandescent black body will take as its temperature changes. If you didn't know, in thermodynamics, a so-called black body is an idealized, opaque, non-reflective body, something like what happens to a needle when you heat it up with a flame. It becomes initially red, then orange, and then if you keep applying heat, it becomes bluish. Please, kids, don't try this at home without the presence of an adult to supervise you. These lines are called isotherm lines, which show the direction in which samples could change color while still preserving the same color temperature. Remember, the color temperature is measured in the Kelvin scale. The higher the temperature, the more bluish the color, and at the other end, the lower the reddish. We are talking about another way of navigating color, using temperature and magenta. The Planckian locus arc defines the changes in color temperature, while moving in the direction of the isotherm lines will affect the magenta component while preserving the color temperature. In Nuke, we have color controls for the temperature and the magenta, so by moving one slider, you still preserve the characteristic of the other. Humans are quite used to this color temperature shift, as our eyes are constantly balancing the temperature of the light we are receiving to make sense of the environment, white balance, and so define the white point of our perception, and we don't even notice. But this point must be established and standardized, so the CIE started defining the different standards to represent what we perceive as white under different lighting conditions. The white light or illuminant. One of the most important for us using RGB color spaces is this one, the CIE Standard Illuminant D65, which is found at approximately 6500 degrees Kelvin in the Planckian locus and correspond roughly to the average midday light in northwestern Europe, comprising both direct sunlight and the light diffused by the clear sky. Hence, it is also called a daylight illuminant, which is why they put the D before the 65, that represents 6500. Those in here are the coordinates in the chromaticity diagram, but it isn't the only one relevant for us. We also have the D50, slightly warmer white, and others not standardized by the CIE, but specifically calculated for certain color spaces, as we will see later. So now that we understand fully the CIE XY chromaticity diagram and how to calculate a color gamut, it is time to focus on the features of the color space. Cameras and displays have been created to reproduce images using a similar process to the human eye, a three-stimuli signal based on the wavelengths of light our cone cells recognize: red, green, and blue, RGB. So those three colors are the three components that are going to be combined to define all colors in the space. The three vertices of the gamut will be represented by each of these components, which we will call primaries, the signals that originate the colors. The position of each primary defines its purity. I don't need to tell you that the closer to the edge, the purer the sample, and so the better. And the wider and more distant they are, the more colors it will contain. So in here, when we connect the primaries, the resulting triangle is the color gamut for this given color space. Now that we have the gamut, let's establish the white point. Here, this is the center of the gamut, the point of no saturation, the appearance of the white light. This color space that we have just represented is the famous sRGB. Those are the coordinates of its primaries and its white point, that, by the way, is precisely the D65 we discussed earlier. This is the color space ruling still today by most of the computer monitors in the world. This is why this color space is so important for us. It's an industry standard. It was developed in 1996 by HP and Microsoft for monitors, printers, and of course, the web. It was then standardized by the International Electrotechnical Commission, or IEC, in 1999. And since then, it has been an industry standard for VFX. Did you know that at its core, Nuke Color Management by default uses an sRGB working space, and for all these years it has been great. But things are changing. Now that we understand what is the gamut, and that is based on the three primaries and completed by the white point, let's go ahead and study the last element that conforms a color space, the transfer function. In color management, there is a function that is an essential part of the color space, which is the transfer function. The transfer function defines the mapping between linear tristimulus values and nonlinear electronic signal value of the image capturing device. So, it distributes every sample of light or exposure captured by the camera or any other acquisition device into its right position in the color space. So, this way, every sensor manufacturer creates a specific transfer function for every model of sensor to optimize its performance to render photographic results, and so the overall ability of the camera to reproduce color. In other words, how the sensor, or the display, is going to distribute the color data to be rightly positioned within the color space. The transfer function for a capturing device is called input transfer, and as you can imagine, there are also output transfer functions designed to convert the values of an image for a target display. Same process, but the other way around. By the way, the trace resulting from that function for all three components of the color model is known as the characteristic curve and defines the ability and features of the camera to capture light, which means the characteristics of that particular digital camera or any other particular capturing device. There are different categories of transfer functions depending on the mathematical operations used to correspond the data. Let's visualize them in the form of lookup tables. The first one is the linear, also known as lin, where the input and the output are the same. It means the signal is not altered. When you visualize something raw with no conversion into a certain color space, you are actually seeing its linear distribution of samples, from normalized 0 to normalized 1 in an arithmetic progression. Computers generate images linearly, as they don't have any electronic signal to be converted, but a mathematical calculation of light. A perfect linear light. Then you have the logarithmic or log functions. They are used for cameras and film scanners as they accurately represent the behavior of light in relation to sensitivity and the perception of detail for the different expositions. The classic Xenon, developed for film scans, and the newer Alexa Log-C are part of this category. The gamma function was originally developed for correcting CRT monitors and then evolved for other displays. It maintains the endpoints of the curve intact, normalized 0 and normalized 1, but remaps the other values in between. Examples of this are the sRGB for computer monitors and the Rec 709 for HD TV. This one belongs to the standard dynamic range world, but now, with modern displays, we are adding new categories that are going to keep in consideration the signals for values brighter than the usual white point of an SDR monitor. So, with a brighter white, we need special transfer functions. So that's why our next two categories fall under the high dynamic range group, and they are hybrid log gamma, or HLG, combining both functions, the logarithmic and the gamma, in one curve, and the perceptual quantizer, or PQ, which is an electro-optical transfer function that allows an HDR signal with a luminance up to 10,000 nits, or candelas per square meter, as we will see later. The use of either function combined with the Rec 2020 primaries has been standardized as Rec 2100. Just to show you the difference between SDR display transfer functions and the HDR ones, here you are a sneak peek of something we will study later in this series, to put in relation the light levels of HDR and the signal value distribution. So, with these groups of LUTs, you can have an overview of the different transfer functions that are used to capture and display data. The question now, to avoid misunderstanding, is to separate the concept of transfer function from the common so-called lookup table, as they are similar concepts, but certainly not the same. LUTs have been part of color handling since the beginning, especially when you have to convert the color space of an image to be visualized into a different display device with a different color space, and even more relevant when you are working with an image based on the color capabilities of a particular display. I think it's time to explore lookup tables. First of all, what is a LUT or lookup table? It is simply an array of data structured by correspondence, like a dictionary, and replace runtime calculations by the computer. In other words, it is a list of instructions to convert the given values or input values into a desired target value or output for every single pixel. In terms of color, it transforms your input color values into other output color values in what is called a remapping operation. LUTs could be pre-calculated in an array resulting from a function, or just arbitrary values stored in the array. So the computer just reads and reassigns the values for every pixel in the image. So we can say the transfer function is the source of a particular type of LUT. But not all LUTs are transfer functions. For example, some LUTs are meant to transform from one color space into another, others simply to apply a creative look, and other uses you like for any fixed transformation of color based on a correspondence for every given value on every pixel in the image. Let's have a look at an easy example for both versions, the pre-calculated LUT and its original function. This is our given RGB image, and for RGB, I just mean color image. We are going to apply to all three channel components the same correspondence of values. This means my lookup table is a 1D LUT. Only one curve represents the operation for all channels. These are all the values from all three channels, from the darkest, normalized 0, to the brightest, normalized 1. This is going to make the calculations easier instead of using the nominal 10 bits values ranging from 0 to 1023. Now, let's create a graphic representation to visualize the LUT. Right, the Cartesian plane again. In both axes, the same scale of numbers in an arithmetic progression, from 0 to 1. The horizontal axis, the x, will represent the input, the original values, and the vertical, or y, will be the output, the resulting values of the LUT. Notice that while the input data states the original values writing in the image file normalize, the highest value cannot be higher than the maximum value allowed by the bitdef. In other words, for example, in a 10-bit image, we say normalized value 1 is the original maximum value, corresponding to the 10-bit 1023 value. So in a 10-bit image, you cannot write a value of, for instance, 2000. It doesn't exist. That's why we are going to have an input from 0 to 1, the maximum normalized value. But the output is a different story. You can create a correspondence above the normalized one, which is, by the way, quite common and widely used to certain file formats, like the log ones. Does it mean you cannot have a LUT with an input value above 1? Well, yes, and even more. With values less than 0, but those LUTs are meant for creative purposes, while in here we are focusing on the LUTs and transfer functions to remap color values within a certain color space for its proper distribution. So for these examples, I'm assuming just the nominal bit depth color positions of a raw image. In any case, strictly speaking, all LUTs behave the same. Input values remap into output values. The first instance is going to be a linear pre-calculated array. Here you are the values. This example LUT has only 3 keys, meaning the rest of the values will be interpolated linearly between the key values by the computer. Let's locate the first array in the graphic. Input value 0 goes up to value 0 in the y-axis, so it stays where it was. The next one, the original value 0.5, the midpoint, goes up to result in 0.5, ending in the middle of the vertical axis. And value 1, the white point, is mapped into the output value 1, the same level of white, as you can see. So if we connect those points, the result is this: a linear arithmetic progression between the input and the output. In other words, the image remains unchanged. We can call this LUT at rest, meaning it isn't changing the image that is being applied to. The precision of the LUT will depend on the number of keys in the pre-calculated array. In an 8-bit LUT, you will have up to 256 keys. So, in an 8-bit image, you will have all its possible values pre-calculated, while the same LUT applied to a 10-bit image with its 1024 values will have only a quarter of the values pre-calculated, and the others will be interpolated linearly, resulting in a loss of precision. So, we have in one hand the fast computational option, the array, but in the other hand, there is a formula that is going to be mathematically precise for every value regardless the bit depth of the image that is being applied to. The function. Let's have a look. The mathematical function for the linear LUT is function of x equals x. The function of x means every input value, and what is after the equals sign is the formula to calculate the resulting value for every given input value, the output, or in this case, y. So if we apply this formula where the output is equals to the input, here you are the result, exactly as before. You can check using the same values we pre-calculated for the array. Here you are. And at the end, the result of the image, same as before. This is a linear LUT. Let's have a look at a more interesting and complex example. We are still using a 1D LUT. Let's position the values. Input 0, the black point, goes up to 0.25. So this means the darkest black we will have in our resulting image will be this gray, a so-called milky black point. Next, the midpoint, 0.5, is going up to 0.875, which means the mid areas of luminance are going to be very bright. And my original value 1, the brightest of my input, is going beyond the output value 1, exactly at value 1.5, meaning is on the super white area. The values my monitor cannot display, and they will be reproduced as just value 1, together with everything that is equals or higher than the output value 1. Have a look at the resulting image, very bright, milky blacks, and the highlights displayed in your monitor as merely white. But we know there is data in those bright areas. So having this LUT associated with the original data writing on the file is actually a good way to store normalized values that represent light beyond value 1 and still being encoded and contained in a certain bit depth. If you are hearing the term bit depth a lot and you are unsure about that, no worries, we will talk about this later. Now, let's have a look at the function that defines this pre-calculated array. As you can see, the formula for the output is quite different. Now, we have to take the input value, expressed as you know as an x, and multiply it by 1.25. And then, after the multiplication, as we learned in school, add 0.25. Same result. Because this function expresses an arithmetic progression, but things are going to get complicated now. In this other example, we have a very different progression. 0 remains unchanged, 0.5 goes up to 0.25, visible darker midtones, and value 1 remains unchanged as well. Look, if we interpolate the results, our line appears to be broken, not a continuous straight line. It means the progression of contrast in the first half of values is different from the progression of contrast in the second half of the output. In both cases, constant progression, but different. And that doesn't look physically plausible. The reason the linear interpolation here is not working well is because we don't have enough density of data. I mean, number of keys in the array to populate the LUT. So instead of using a pre-calculated LUT with a limited number of points, let's have a look at the function that generated those 3 points. Here you are. This is a power function of x. So the result is not linear. It's logarithmic. Not a straight line anymore, but a curve. This is the resulting image. Only the midtones have changed. Notice the color chips in the image of Marcy are intact, as they are value 1 or 0 in each RGB channel. And applying the formula, value 0 and value 1 always remain unchanged. This shows the overlap of the array against the function representations. Quite different, aren't they? So, how do you bake the results of this curve into an array? I'm glad you ask, because you have to get an array with the pre-compute result of a key for every single value in the target bit depth of the image. So, 256 keys with their respective values for an 8-bit image, 1024 for 10 bits ones, and so on. Maybe we can express the LUT simply with the function and avoid to read and write so much data. Besides, the function is universal for any bit depth. And things are going to get big when you get an array for a 3D LUT, meaning you have an array or function for every channel. Like a cube in 3D, each of the 3 axes represents a color. So each component of the RGB will have their own specific array or function. This is a live view of the color transformations illustrated as a LUT. As I said before, LUTs can be used also to define a certain creative look, to apply any kind of primary color transformation. Primary color transformation means the correction is applied to every pixel, and this is in opposition to secondary color transformations, where the color manipulation is applied to just an isolated group of pixels. So a LUT is a fixed color transformation based on a remap of the given values of every pixel in the image, and used for different purposes. I think we should go back in time again to understand how we have been managing color traditionally, by applying LUTs to convert from one color space to another, also known as color transfers. With this, you are going to get an overview of why the change is necessary. So, welcome to the brief and oversimplified story of the color transfer odyssey. In the beginning, they were film cameras, and they shot in film negative stocks. All you need to do is to develop the film negative and convert it into positive. Apply a light to it, and voila, cinema projection. It was all analog, a physical support, and everybody was happy. But if we wanted to put a film on TV, we needed to convert the physical support into an electronic signal. So we used a telecine, practically a video camera that taped the negative recording against a light. So we have a magnetic support that is still analog. Not perfect for a few reasons, but still, everybody was quite happy with it. But then, people started getting personal computers accompanied, of course, by CRT monitors, which stands for cathode ray tube. Roughly the same technology as the TVs of the time, so the image capabilities of both TVs and PCs behave the same. So any image document requires a correction made by the software attempting to visualize it, more or less correctly in the CRT monitor, and I mean more or less because every CRT monitor was built without a standard criteria for color, and every software was doing its own thing to represent color. Then computers and monitors evolved, and finally everything complies with the newly established sRGB color space. So my image is going to be displayed correctly as the monitor and the software are aligned in terms of color. And so the website's full of images I browse on the internet. In the meantime, we are still in the 90s. The film scanner has been invented. The digital intermediate is born, used for the first time to digitally restore and remaster Walt Disney's 1937 classic Snow White and the Seven Dwarfs. The process is also known as DI, as we scan the original negative, converting it into Xenon file sequences in gorgeous 10 bits, higher bit depth than the 8-bit sRGB we use for watching videos of cats on the internet. Everything was processed in digital after the scan, but at the end, for the delivery, we print it back again in a film strip to be projected in analog as before. So the digital part was just in the middle, until digital projectors became good enough, affordable, and popular, without mentioning the contribution of the stereoscopic boom created by James Cameron's Avatar. Digital cinema changed the rules also in the chain of distribution, as film rolls didn't need to travel. The new digital cinema packages, also known as DCP, were transmitted over the internet. Cinema was becoming entirely digital, but not end-to-end just yet, until digital cameras landed. No more need to scan film negatives. Images from digital cameras, though, were converted into the same Xenon file sequences we use for film scans to keep a consistent workflow. And then the TV became digital and abandoned the less ecological CRT to become LCD. But during the times of transition to digital, they had to build inside the software of the digital TV the same defects of the image reproduction that CRTs had natively. So everybody could see the same corrected signal able to be reproduced by a crap old system. A problem that the LCD didn't have natively, but had to be embedded for compatibility purposes. A smart move for consistency, but a headache for everything else. And since the TV became digital, meaning they have a computer inside, TV started evolving at the same rate as computers. So we stepped from standard definition, the old NTSC or PAL, to the World Unified HD in their two versions, 720p and 1080p, but both with the same color space, a tweaked version of the sRGB, a recommendation made by the International Telecommunication Union that became the standard for HD TVs, the recommendation number 709, or ITU-R BT.709. That's a long name. Let's just call it Rec 709. It maintains the same primaries and white point of the sRGB, but changing slightly the gamma, its transfer function, to represent the images with a better color quality in these new devices. But why stop evolution here if we can get bigger resolutions, bigger color spaces, and higher bit depth? Computers get better and more affordable. Technology evolves. The pursuit of image quality never stops. And here we are at 4K HDR TV. But just when the trend was bigger is better, and while the market was focused on making bigger screens and more powerful projectors, people decided to watch contents on their phones and tablets. Portability versus bigger screens. So the process that once was called digital intermediate became significantly more complex, with elements coming from very different sources needed to be visualized for processing on the same sRGB monitors, but to be delivered for displays with the same capabilities of the computer monitors and for better screens. So how can you work colors, bit depths, and dynamic ranges that you cannot visualize? Of course, using LUTs to convert from a device to another device, depending on where the image was generated and where we want to transfer it now. Yep, that's a lot of LUTs. Furthermore, once the project is finished and the master final delivery is archived, what will happen in a few years' time when displays get even better? Our precious material that came at a high cost will become simply obsolete. This mess relies on one single problem. All corrections to adapt the content to be correctly visualized on the screen implied changing the actual data of the images to be adapted to every display. So as soon as the technology changes, our files must change every time to adapt to that new technology, to the display. This is known as display referred workflow. But there is another way, and it's called scene referred. Let's have a look now at how the scene referred workflow actually works. The first thing is to choose the master color space, one wide enough to contain all the gamuts of the files we are going to ingest. High dynamic range compatible these days is a must, so you should keep that in mind as well. The unified color space doesn't depend on any display. It is just a mathematical container of color data. It is time to ingest our footages. So we will need to apply an input transform to convert the raw data or the source material from each device into the unified color space. Notice that the CGI could be rendered directly encoded into the unified color space, so it doesn't need to be converted. But of course, you could always convert it to that target unified color space if you already render in the traditional sRGB linear. The thing is, if you can render it directly into the unified color space, please don't make any useless conversions. We will discuss color transformations in Nuke later in this course. Now, everything is in the same color space, so they all obey the same rules: same gamut, same white point, and same transfer function. This last one expected to be linear, but we will talk about that later. And please keep in mind that the fact all footages are inside the same gamut doesn't mean all images from every source use the whole gamut of the color space. For instance, a video recorded with an iPhone will be allocated in a smaller range of the master color space in relation to the footage captured with, for instance, an Arri Alexa. So, the process of placing all images in one single color space won't improve their quality, but it won't lose it either, and will make the handling of color the same as any other capturing device. No special rules. Like what happens inside Nuke when you work with images with different bit depths. All images handled within Nuke workspace are automatically converted into 32-bit floating point, regardless of its original source bit depth, so you can mix them without needing to align their bit depths. Which means the artist could apply a look from an external file that obeys the rules of this master color space to any image in the unified color space. At this point, any color transformation to the images will behave the same for the iPhone images or the Arri Alexa captures, respecting each source capabilities. But in terms of color manipulation, they all behave the same. So we have all the data intact in our master footages, together with the look intent, so when the footage moves to other departments, they are all aligned in terms of what everybody sees in their screens, and they have access to the footage in the same color space, always maintaining the creative look intent. In our case, for the VFX department, we can, for instance, read the footage in Nuke, apply to our viewer the appropriate display transform according to the monitor or projector or TV we are using to visualize the composition, and also apply to the viewer the look intent defined for this shot. So we are going to have on our screen the image as the filmmakers intended it to be, while our footage is still intact. They are just visualization corrections applied to the viewer. After VFX have completed their job, everything moves to DI. That, by the way, DI still stands for Digital Intermediate, even though the whole process is digital, but it's a reminiscence. The final grade will be applied, keeping in consideration the look intent, and after the grading process, a display transform will be applied for every destination display device, each one in their own color space and features. Of course, with the transfer to certain narrower color spaces, the grade may need to be tweaked to adapt to that color destination. For instance, Pixar's colorist Mark DiNicola, while working on the film Cars, had to make adjustments to the grading of the protagonist, Lightning McQueen, because he was displayed quite differently from the cinema version to the TV, as the primaries of each gamut are different, and Mr. McQueen's shiny varnish is purely red. So, once the grading is complete and all deliveries have been handled, it's time to archive. The masters will be collected in the unified scene-referred color space, and the grading sessions will be saved as color transformations. So in the future, we could always get back and restore everything and deliver for those devices that are not invented yet. So this workflow is future-proofed. So as you can see, in here, there are only 2 color transformations happening to the footage. One at the beginning and another at the end for each delivery. What happens in the middle is just a visualization transform, but the footage across the whole pipeline always remain untouched in terms of color space. Essentially, the main difference between display-referred and scene-referred color space workflows is this. In the display-referred instance, you have the footage and then the color transformation is applied in relation to the display, so it can be shown correctly. While in the scene-referred instance, the color transformation is applied in relation to the footage, agnostically from any display. As a result, in the display-referred instance, you have to apply a lookup table, a LUT, to convert the color from a color space into another for every footage for every display, ending with a lot of transformations and a high risk of inconsistency and a margin for error. While in the scene-referred instance, you convert every footage into the master color space, and from there you can simply adapt the visualization of the footage for a target display, simplifying the whole process and ensuring everyone is on the same page without compromising the footage across the whole pipeline. In conclusion, the 3 key elements of the RGB color space are 3 primaries to define the color gamut of the color space, the vertices of the triangle. The white point that defines the center of the gamut, the point with the lowest chromatic intensity, the minimum saturation, or simply what we perceive as white. And the transfer function that defines the mapping between the linear tree-stimulus values and the nonlinear electronic signal values, the distribution of the color samples data within the color space.